Dear students, in this lecture we define kernel and range of a linear transformation. First we define kernel of a linear transformation. Now let T from V to W be a linear transformation. Then the set of all vectors in V that T maps to a zero vector in W is called kernel of T, and it is denoted by kernel of T. Therefore, kernel of T is the set of vectors U belongs to V such that T of U equal to zero vector in W. Now we define range of T. Now let T from V to W be a linear transformation. Then the set of all vectors in W that are images under T of at least one vector in V is called as a range of T. It is denoted by R of T. That is, range of T is the set of vectors W belongs to W such that W is equal to T of U for some U belongs to V. Now we note that if T from V to W is a zero transformation, then kernel of T equal to whole space V, and range of T is just the zero vector of W. Similarly, if I from V to W is an identity transformation, then kernel of I equal to singleton zero vector of V, and range of I is whole vector space V. Now we prove a theorem which states that if T from V to W be a linear transformation, then kernel of T is a subspace of V and range of T is a subspace of W. First of all, we prove that kernel of T is a subspace of V. Now since T of zero vector in V is equal to zero vector in W, clearly zero vector of V belongs to kernel of T, and therefore kernel of T is non-empty. And if U and V are any two vectors in kernel of T, then T of U equal to zero vector in W as well as T of V is zero vector in W. Therefore, T of U plus V, which is T of U plus T of V, equal to zero vector in W plus zero vector in W, which is nothing but zero vector of W. And here we get T of U plus V equal to zero vector of W, and hence U plus V belongs to kernel of T, and therefore kernel of T is closed under vector addition. Similarly, for any scalar K and U belongs to kernel of T, T of K into U equal to K into T of U, which is equal to K into zero vector of W, which is equal to zero vector of W, and therefore K into U belongs to kernel of T, and therefore kernel of T is closed under scalar multiplication, and therefore from 1 to 3 we get kernel of T is a subspace of V. Now we prove that range of T is a subspace of W. Now since T of zero vector in V equal to zero vector in W, zero vector of W belongs to range of T, and therefore range of T is non-empty. Now let W1 and W2 be any two vectors in range of T. Then by definition of range of T, there are U1, U2 belongs to V such that T of U1 equal to W1 and T of U2 equal to W2. Now since U1 and U2 belongs to V and V is a vector space, U1 plus U2 belongs to V. Therefore, T of U1 plus U2 belongs to range of T, and T of U1 plus U2 is nothing but T of U1 plus T of U2, which is equal to W1 plus W2. This belongs to range of T, and therefore we proved that range of T is closed under vector addition. Now for any scalar k and u1 in V, k into u1 belongs to V. Therefore, T of k into u1 belongs to range of T. This implies k into T of u1 belongs to range of T. This implies k into w1 belongs to range of T since T of u1 is w1. And therefore, we get that range of T is closed under scalar multiplication. And therefore, from 1 to 3, we get range of T is a subspace of W. And hence we have proved that kernel of T is a subspace of V and range of T is a subspace of W if T from V to W is a linear transformation.